Hi, I'll present a paper cache timing attacks on AES. This study demonstrates how an attacker can recover AES encryption keys by analyzing execution time variations caused by CPU cache behavior. We will start with an introduction and background on AES encryption and cache timing attacks. Then we'll go through the experimental setup and how the attack works, followed by its limitations and key takeaways. Encryption plays a critical role in securing modern digital communication, and one of the most widely used encryption algorithms today is Advanced Encryption Standard. AES is used everywhere from securing internet traffic, online banking, and cloud storage to protecting sensitive data. Because of its strong mathematical foundation, AES is considered secure against brute force and traditional cryptographic attacks. However, security doesn't just depend on the encryption algorithm. It also depends on how it is implemented in software and hardware. Even though AES is mathematically secure, certain implementations of AES can be vulnerable. Unlike traditional attacks that try to break encryption mathematically, timing attacks exploit execution time differences to extract secret information. Modern CPUs use caches to speed up memory access. When data is stored in the cache, it can be accessed much faster than if it has to be fetched from main memory. This means that an attacker, by carefully measuring how long an encryption operation takes, can infer whether certain data was in the cache or not. And if the memory access pattern depends on the secret AES key, timing variations can reveal the secret key related information. This is a critical vulnerability because an attacker doesn't need to access to the encryption process or the secret key. Instead, they can simply observe execution times over many encryption operations and use statistical analysis to reconstruct the encryption key. This is what this research demonstrates. AES is a symmetrical encryption algorithm. When we say symmetric encryption, we mean that the same key is used for both encrypting and decrypting data. Another feature of AES is it breaks data into 128-bit blocks and encrypting each block separately. No matter how big the file or message is, it gets divided into 128-bit chunks, and AES encrypts them one at a time. The strength of AES comes from something called a substitution permutation network, which is a fancy way of saying that each round of encryption mixes up and replaces the data in a structured way. This ensures that even the smallest change in the input completely alters the output, making it difficult for attackers to figure out the original data. To make this encryption process more secure, AES uses a secret key that can be 128, 192, or 256 bits long. The longer the key, the more secure the encryption, but also the more processing power it takes. Depending on the key size, the data goes through multiple rounds of transformation. The first step of encryption is key expansion. Since this algorithm uses a different round key for each encryption round, the original key is expanded using the AES key schedule. This process generates a set of round keys which are used in each stage of encryption. Before starting the main encryption round, AES converts the plain text into a structured format called the state array. The 16-byte plain text is arranged into a 4 by 4 matrix by filling the matrix column-wise. Once the state array is created, it is XORed with the first round key. This is called add round key set. Its main encryption round consists of four transformations. First, we have byte substitution using xbox, where each byte in the data block is replaced using a predefined lookup table called the xbox. This step adds non-linearity to the encryption, ensuring that even a small change in input results in a completely different output. Next is row shuffling, which rearranges the data by shifting each row of the AES state to the left by different amounts. This prevents each column from being encrypted independently and makes sure changes in one part of the block affect the entire encryption process. Then we have column mixing for diffusion. Each column in the data block is transformed using matrix multiplication in column field arithmetic. This step spreads out the influence of its bytes, ensuring that every part of the ciphertext depends on multiple parts of the plain text. Finally, we apply key addition. The state is XORed with the round key derived from the main AES key. This guarantees that encryption is directly tied to the secret key, making it impossible to decrypt without knowing the key. The final round follows the same steps but skips the mixed columns transformation. The reason is that AES decryption must be the exact reverse of encryption. If we apply mixed columns in the last round, the decryption process would require an extra step to undo that transformation. By skipping mixed columns in the last round, we ensure that the decryption process mirrors the encryption steps perfectly. This allows decryption to reverse its transformation in the correct order. Now that we understand how AES encryption works, let's see how attackers can find weaknesses not by cracking the encryption but by measuring how long it takes to run. This method is called a cache timing attack. Modern CPUs introduce memory hierarchy to speed up memory access. The idea is simple. When the processor needs certain data frequently, it stores the data in a small, fast memory area called the cache instead of fetching it from the much slower main memory. This makes programs run faster, but it also creates a side channel vulnerability that attackers can take advantage of. The key idea behind the cache timing attack is that time it takes to access data depends on whether the data is already in the cache or not. An attacker can precisely measure execution times and use this information to figure out which data was accessed. Over time, they can use this pattern to infer secret information like AES encryption keys. To better understand how cache timing attacks work in practice, let's look at an example that visually demonstrates how timing variations can leak sensitive information. This graph demonstrates how an attacker can distinguish between cached and uncached data based on response time. The pink distribution represents response times when an image is cached, meaning it was retrieved quickly. The blue distribution represents response time when an image was not cached. The dashed line shows a clear separation between these two cases, meaning an attacker can determine whether a particular image was cached just by measuring response time. The targeted server configured to perform AES 128 encryption using the OpenSSL library. The server was running on an Intel Platinum 3 processor. The attacker did not have access to the encryption key. Instead, they relied on measuring how long the server took to encrypt different inputs. The server accepted UDP packets from a client. These packets contained random data, and the server responded with an AES encrypted version of the data. The key used for encryption was generated by a secure random number generator in Unix-based system. The goal of this experiment was to analyze execution time variations in AES encryption and use them to extract the secret encryption key. The attacker used a specially designed AES server and monitored how different inputs affected execution time. Let's go step by step to understand how the attacker extracts the AES key using timing variations. The attack works because AES implementations often use lookup tables, which interact with the CPU cache instead of performing each encryption step with direct mathematical operations. Many AES implementations use pre-computed lookup tables called T-table. This T-table stores values for subbytes and part of mixed columns transformations, making the encryption process faster. However, this optimization introduces a security weakness because memory access times are not uniform. The first step of the attack is measuring execution time. To do this, the attacker sends UDP packets with different plain text inputs to an AES encryption server. Each time the server receives a packet, it encrypts the plain text and sends back the encrypted results. The attacker doesn't need to see the actual encrypted data. Instead, they record the execution time using a CPU cycle counter. The way AES looks up values in the T tables depends on both the input plaintext and the secret key. By analyzing execution time differences caused by cache behavior, the attacker can gather potential values for the AES encryption key. With an understanding of how execution time leaks key-related information, we can examine how the attacker systematically analyzes these time variations corresponding various inputs. By modifying input values and measuring encryption times, the researcher identified patterns that expose key-dependent memory access behavior. The following graphs The following graphs from Figure 5.1 to 5.3 demonstrate this process in detail. The leftmost figure focuses on the specific byte of input data, the N13. The attacker tested different values for this byte and recorded the encryption time for each case. The x-axis represents the possible values for this byte of input from 0 to 255. In this case, a clear pattern emerged. Some values resulted in significantly longer execution times. This happens because certain values cause cache misses, forcing the CPU to fetch data from slower memory, making AES run slower. By analyzing this timing data, the attacker discovered that the longest execution time occurred when the input byte followed the relationship N13 equals K13 XOR 8. This means that they could reverse the XOR operation to extract the corresponding key byte. The figure 5.2 takes this method a step further and applies it to N5, but this time the results look a little different. Unlike N13, which showed a single peak at a specific value, N5 creates a wider range of timing variations. This suggests, this suggests that multiple values of K5 XOR N5 cause cache misses, making it harder to determine K5 precisely. However, by analyzing a large number of samples, the attacker can still narrow down possible key values for K5. Finally, figure 5.3 looks at N15, and here we see a pattern similar to figure 5.1. There is a distinct peak in execution time, which means that K15 is strongly correlated with a specific N15 value. Just like with K13, this allows the attacker to extract another byte of the AES key. By applying the same process to all 16 bytes of the AES key, the attacker gradually reconstructs the full key. Some bytes like K13 and K15 in the previous example are recovered directly from execution time peaks, while others require statistical filtering over many measurements. Once the attacker has a small set of candidate keys, they can test them using known plain text to determine the correct AES key. The results in this slide represent the output of the correlate program, which processes the timing data collected from the attack and helps extract the AES key bytes. The table consists of three important columns. The first column indicates how many possible key values remain after timing analysis. The second column is the key byte index from 0 to 16. And third column consists of the most likely candidates for that key byte inferred from timing variations. For byte index 3, we see only one candidate value. This means we have fully recovered that byte with high confidence. For byte index 13, we can see 16 possible values. While we haven't identified the exact byte, the attacker has significantly reduced the search space. The fact that an attacker can extract an encryption key shows just how dangerous timing attacks can be. Because of this, the author strongly emphasizes the need for constant time AES implementations. The key weakness in T-table based AES encryption is that execution time varies depending on memory access patterns, allowing attackers to infer key-dependent information. To prevent this, cryptographic functions must be designed to always take the same amount of time, regardless of the key or the input. If there is no variation in execution time, attackers have nothing to measure, making tiny attacks. While this attack successfully demonstrated how timing variations can be used to extract AES keys, it does have some important limitations. First, this experiment was conducted in a strongly controlled environment, meaning it was tested on a dedicated machine with minimal interference. However, real-world servers operate under very different conditions. For example, on an actual network, we have variable latency, unpredictable system roles, and multiple background processes running at the same time. These factors introduce noise that could make precise timing measurement much harder. The second major limitation is that modern AES implementations have improved significantly. One of the biggest improvements is the shift to constant time execution, which eliminates the timing variations that make this attack possible. For example, OpenSSL and many other cryptographic libraries now implement AES using constant time operations. This makes it nearly impossible for an attacker to infer key-dependent timing differences. While AES is a strong and widely trusted encryption algorithm, Its security heavily depends on how it is implemented. This study highlights how even a secure algorithm can be vulnerable if executed improperly. This research demonstrated how timing variations in AES execution can be used to extract the secret encryption key. By measuring how long AES encryption takes for different inputs, the attacker was able to correlate execution time with secret key dependent memory accesses. This allows them to reconstruct the AES key. This proves that cryptographic security is not just about mathematical strength, it's also about how the algorithm interacts with the system's hardware, especially memory. This study reinforces the importance of constant time execution in cryptographic software. If encryption operations take different amount of time depending on the key or input, an attacker can observe these differences and extract secret information. By simply measuring encryption execution times, an attacker can extract secret keys without accessing encrypted data or brute forcing the key. This attack highlights why modern cryptographic implementations must be carefully designed to eliminate timing-based vulnerabilities. With that, I conclude this presentation. Thank you for your time, and I'd be happy to take any questions.